In today's lecture, we shall talk about the concept of energy return on investment, abbreviated as EROI. It can be treated as a supplementary metric to energy payback time. The topics for this lecture include the definition of energy return on investment and its comparison with energy payback time, the PV system performance landscape, and some energy return on investment aspects. In general, the concept of our commonly used energy return on investment is actually the energy return on energy investment. For this reason, there have been different acronyms used in literature, as is shown here. The most commonly used one is EROI. Literally, energy return on investment is the ratio of energy return or energy output divided by the energy investments of the analyzed system. Here is a streamlined energy systems diagram for a PV power system. The IRR represents the total solar irradiation over system's lifetime. The PE indicates the primary energy directly harvested over system's lifetime. The EINV stands for energy investment to build, operate, dismantle, and recycle at the end of life the PV system in terms of its primary energy demand. The out EL implies the total electricity produced over system's lifetime, while the S denotes the energy dissipated to the environment. Finally, the green frame defines the system boundary of the so-called net energy analysis. The net energy analysis is a structured, comprehensive method of quantifying the extent to which a given energy source can provide the net energy gain to the end user. The energy return on investment is the principal indicator from the net energy analysis. The methodology guidelines of the net energy analysis are elaborated in the listed reference file. Now, we can define the formula as is shown here. The energy return is the numerator, which is expressed by the total electricity generation divided by the grid efficiency. The overall energy investment is the denominator. It is noteworthy that in the calculation of both the energy investment and the energy return items, one needs to pay special caution to factor that needs to be included or excluded to avoid misguided interpretations. In previous lecture, we discussed the concept of energy payback time. Its formula is reported here as well. The correlation of energy return on investment and energy payback time can be expressed via the system's lifetime. In this perspective, we could treat energy return on investment and energy payback time as two complementary metrics. However, there is one key difference between these two metrics. Energy return on investment looks at the overall energy performance over the PV system over its entire lifetime, while energy payback time only concerns how long it takes for the PV system to return an amount of electricity that is deemed to be equivalent to the primary energy investment. This slide shows a summarized PV system performance landscape. Be aware, data are from the previous decades and current efficiencies are much higher. The counterplot of energy return on investment are shown as a function of electricity investment and module efficiency. Two types of balance of system scenarios are still studied. The figure A on the left-hand side corresponds to a high BOS scenario, and the figure B on the right-hand side is a result from a low BOS scenario. The dashed line indicate outliers of each technology group. As can be seen, the energy return on investment is vastly different in the two scenarios. However, thin film technologies perform better in both cases. Such technology include cadmium telluride, CIGS, and amorphous silicon. As for the crystalline silicon PV technologies, their high efficiencies are somehow compensated by the cost of higher energy investment or demand for the total system. The above-mentioned energy return on investment is essentially an integrative energy return on investment. It considers all the energy inputs and outputs to from the system at once. Therefore, the energy return on investment value does not distinguish between the different phases over the total period from construction to operation to decommission and finally recycling and recovering materials. The contributions of these phases to the total energy investment and to the total energy return can be determined. A more realistic representation of the dynamic reality of a generalized energy system is illustrated in this figure. The subscript of C, OP, and D represent construction, operation, and decommission, respectively. Along with the different phases of the life stage, dynamic modeling can also be applied. Specifically for PV system, because almost of the energy investment is clustered at the beginning of the life cycle, while the energy output is still spread over much longer use phase. Its dynamic energy return on investment is initially lower than the integrated energy return on investment. At a certain moment, net energy can be gained. Then, the upfront energy investment is overcompensated by the total amount of electricity produced by the PV system. For the dynamic approach, a function of energy return on investment over time can be used. Besides, another metric of the so-called power return on investment has been proposed to accurately refer to the dynamic evaluation, because the dynamic energy return on investment in fact measures the ratio of two power flows. To recap, in today's lecture, we firstly spoke about the definition of energy return on investment. It is obtained from the so-called net energy analysis. We discussed the formulas to calculate energy return on investment and related its value to the previously discussed energy payback time. They are complementary metrics, and the difference between these two matrices is also tackled. The counterplots of energy return on investment of different PV systems were discussed in both high and low balance of system scenarios. The thin film PV technology represents the highest energy return on investment potential, and the high energy investment for crystalline silicon PV is somewhat compensated by its high efficiency. Lastly, we spoke about the modeling aspects of energy return on investment calculation. The integrated energy return on investment is normally utilized, meanwhile the dynamic energy return on investment or power return on investment is also proposed.